Good afternoon, everyone. So I'm Noel, and I'm currently a PhD student at École des Mines Saint-Etienne in France. So in this presentation, I'm going to describe a language to define the design of a linked data platform. So this work was done together with Antoine Zimmerman, who is actually here, and Olivier Boisier. And Antoine and Olivier are both my supervisors. And this work was done in the context of the Open Sensing City project, whose aim is to foster and facilitate the exploitation of smart city data in the open data context. So we have the W3C Linked Data Platform 1.0 standard from the W3C. So basically, this standard is a marriage between the linked data principle and the REST principle. And the aim of this standard is to standardize RESTful access to linked data. There are numerous advantages of doing so. For example, the HTOS in LDP enable decoupling LDP server and clients, enable development of generic LDP clients. So in short, LDPs can be used to provide a homogeneous view and access to data, facilitating both the task of data publishers and consumers. For example, data publishers can publish their data without having to bother about the tools and other stuff that consumers are going to use. Consumers can have their tools built and application built and clients without bothering how data publishers are going to publish their data due to the standard. So the LDP standard consists of two main parts, the domain model and the interaction model. The domain model provides different types of resources, namely the RDF resource and non-RDF resource. And then there is a special type of resource, which is the container, whose aim is to group resources. And we have different types of containers, basic, direct, and indirect. And the speciality of basic container is that it can contain only resources that are RDF resource and non-RDF resource. And related to the other type of container, there are other properties which in this language we do not consider. For now, in our language, we consider only RDF resource and basic container. And we refer to an RDF resource which is not a container as a non-container, and we refer to basic container simply as containers. And then the LDP standard consists of the interaction model, whose aim is simply to interact with LDP resources to manipulate them through HTTP methods. And for example, specify the different form of HTTP requests and responses, headers that the requests and responses should contain, status code, and so on. So for now, LDP implementation consists of two main categories. The first one, LDP resource management system, which can be thought of as a repository for storing LDP resources, on top of which there are read and write operations to manipulate LDP resources. And then we have LDP frameworks that are basically APIs to facilitate development of LDPs. They would include like helper methods, generic class templates that can then be instantiated in specific use cases for specific situations. But the problem is that for now, current LDP implementation, they are very basic. They require lots of manual work. For example, the LDP standard requires data design and data deployment, and the current LDP implementation, they provide no automatic support, neither for design nor for deployment, even if the data is already in RDF. So our solution is to provide a language, the LDP design language, which is LDP-DL, to describe the design of an LDP separate from any deployment or any implementation. And then we are going to use description in that language to generate an LDP. So based on this context, so I'm going to provide an overview of LDP-DL. I'm going to describe the syntax and semantics, and then describe the implementation, and finally the evaluation, the different experiments we did. So let's consider this as, let's throw that this is a big RDF graph whose only a portion I've shown here. It uses the DCAT vocabulary, and it uses several clauses and properties related to the DCAT vocabulary. And what we want is, we want to expose this via an LDP. We want to expose resources from this graph via an LDP. And there are a number of questions that we need to ask ourselves when doing this. The minimum set of questions would include, for example, what are the different LDP resources, in which containers the resources are going to be, what are the content of LDP resources, if they are RDF source, what is the graph of the RDF source, that is a non-container, and if they are basic container, what is their graph, and what do they contain, that is their members. So this is a possible answer that we can obtain from with LDP-DL. That is, we have an organization of LDP resources, and also on dereferencing an LDP resource, we obtain a graph. So using LDP-DL, we are able to define the design, the organization of different LDP resources, the content of, that each LDP resource should contain with respect to an RDF graph. So this is the abstract model of LDP-DL. So an LDP-DL design basically contains a set of container map and non-container maps. And let's position this abstract model with respect to the example that we have been using. So let's assume that in the LDP here, every resource that contains another resource is a container, and these are non-containers. They do not contain other resources. So our language allows us to describe these containers and non-containers using the construct container map and non-container map. And then, so the idea is that for every resource from the RDF graph, we are going to generate an LDP resource that is going to describe the LDP resources here. So for example, for DEX Paris catalog, it describes Paris catalog. For BSXML, it describes BSXML here, and many resources from the LDP here, they describe RDF resource here. And the LDP resource for which the RDF resource for which an LDP resource has been generated is referred to as the related resource of that resource. So for example, the LDP resource DEX Paris catalog, its related resource is X Paris catalog. So similarly, there are resources here having related resource here, which they describe in their graph. And for example, if we dereference the content of DEX Paris catalog, what we obtain is an RDF graph containing the description of the related resource and also some members. And these members also, they can have related resource, and then recursively they are going to contain a portion of RDF graph that describe resources here with other members. So to be able to identify related resources, we have the construct resource map, and then using related resources, we are going to generate LDP resources and their graph. So for this, we have the construct resource map. The query pattern here allows us to identify the related resource, and then the construct query allows us to generate the graph of these LDP resources. And then the container map and non-container map, they use the resource map to generate their containers and non-containers. And then finally, to describe members of containers, container map allow nesting of container map and nesting of non-container maps. So now, regarding the semantics, the aim of LDP-DL semantics is to associate an LDP dataset to a design document. So what is an LDP dataset? It's a structure that we introduce to organize LDP resources. So basically, it stores LDP resources. So the aim of the semantics is to associate an LDP dataset to a design document with respect to an RDF graph. And so an LDP dataset is basically a set of name graph that represent non-containers, and then a set of container structures that represent containers. So name graph represent non-containers, container structures represent containers. And a name graph ng is actually where n is the IRI of the non-container, and g is the RDF graph obtained on dereferencing the non-container. And then a container structure NGM is actually a container where N is the IRI, G the RDF graph obtained on dereferencing the container, and M is the set of IRI representing the members of a container. So now let's try to I'm going to take an example of the RDF graph, and this is a design document in LDP-DL, and this is the resulting LDP that we want to obtain. So I'm going to take the design document, evaluate it on the RDF graph to show how do we arrive at the resulting LDP. So the idea in the LDP is that we want to have a container to describe the catalogs here. So what we do is that we have a catalog container map which has a resource map, and the resource map, it has a query pattern and a construct query. We use a query pattern because we already know to which variable we want to project the solution. So this variable here relates to the related resource. So with this query pattern, we identify the related resources. So for example, the evaluation of this query pattern on this graph returns two solutions, Paris catalog and Toulouse catalog. And then for each of them, we create a new resource, that is this one and this one. And for example, let's consider the first solution. For this solution, what we do is that we consider the construct query. So for this solution, first we generate a new resource, and then we bind the new resource to the variable new, and then when evaluating the construct query, we evaluate the evaluation of this construct query on the RDF graph here is parameterized by these two bindings to finally generate the graph of Paris catalog. Similarly, for example, if we had to do this for Toulouse catalog, it would be, for example, for the second one. So we would have this variable, a variable dex Toulouse catalog for new, and then we would evaluate the construct query on this RDF graph to generate the graph of Toulouse catalog. So now suppose that for the members of Paris catalog, we want these members to describe data sets of Paris catalog, because remember that this LDP resource here describes this resource, so we want the members to describe its data sets. So for this, we have a data set container map which has a resource map, but in this time, the query pattern not only contains a reserved variable for us to project the related resources, but it also contains a reserved variable, which is the parent variable. And when evaluating this, the idea is that to identify the appropriate related resource for the Paris catalog, which is this one and this one, we have to do this in the context of Paris catalog. Because, for example, the same construct is going to be used to identify the related resources of Toulouse catalog. So the evaluation of this query pattern on this RDF graph is done, is parameterized by the parent variable, which is actually the related resource of the parent LDP resource. So this, the evaluation of this query returns us these two members, and then for these two members, as we did in the previous for catalog resource map, for these two members, we create two LDP resources and generate their graph. So this is a brief overview of the semantics. And regarding our implementation, so we have not yet automatized the design phase so far. So we have to write the design. So consider this as a design in LDP-DL. So we are going to consider a set of RDF source. And then we have an LDPizer, which is basically an LDP-DL interpreter. And so we are going to evaluate the design document with these data sources here. And also, it is possible to have non-RDF source. In this case, using the language, we can specify a lifting rule written in Sparkle Generate for now for these non-RDF sources. And the idea is to generate an LDP data set, and then to deploy the LDP data set on an LDP server, we have an LDP dataset deployer, which is completely agnostic of the implementation. So what it does, it simply generates post requests for LDP resources in the LDP dataset. And then we have a dedicated LDP server we have developed that can directly consume LDP dataset to expose LDP resources. And then we also have a dynamic LDP dataset, that is different from the LDP dataset, in that in the LDP dataset, we store the graph. But in the dynamic LDP dataset, what we do is that we store the compile construct query, that is the construct query obtained by replacing the variable bindings. We do this so that we can treat real-time data sources, dynamic data sources, or even static one that we don't know whether they are going to change or not. And then finally, we have a small application, LDP browser, that we can use to browse different LDP, and it is completely independent of the implementation of the servers as well. So our evaluation consists of performing experiments for showing the different characteristics and properties of the language and the approach in general. So in our experiments, we use different design documents to operate on heterogeneous and real-time data sources, and we generate over 100 LDPs. And in these experiments, we show the reusability of the design by using the same design on different data sources. We show the flexibility of our language by using LDP-DL to describe different designs for the same data source. And then we show the loose coupling of our approach by generating different LDPs using the same design from different data sources. And then we deploy these LDPs on different implementation, so we are able to have LDPs of the same design from different data source using the same design. And then, as I mentioned, so far we have to write our design, but what we do is that to partially automatize the design phase, we provide generic designs that can be applied on RDF graph that uses RDFS vocabularies. So we can think of having a generic design for scores for different other vocabularies. And we also deploy LDPs on reference LDP implementation. So far what we have tried is Apache Marmota and Gold. And we also show that we are able to deal with heterogeneous and real-time data sources. So to conclude, so in this work, we provided an LDP design language to describe the design of LDPs separate from any implementation or deployment scenarios. We have implemented the LDP-DL interpreter. We have an LDP dataset deployer. We have dedicated servers. We evaluated our approach and language with respect to several properties in several experiments. So the future work would probably involve like extending LDP-DL to other types of resources, because as I mentioned, for now we only consider RDF source and basic containers. So basically we would like to extend to direct, indirect, non-RDF source. And then we intend to consider other design aspects, for example, access rights. And then since we have theorized the state of an LDP as the LDP dataset, what we intend to do is, for example, to have the different LDP operations like HTTP GET, put and post and so on. We want to theorize this operation as an algebraic operation on the LDP dataset. And then finally, we also intend to support pagination, which is a desired feature for large dataset. So thank you for your attention. If you have any question, feel free. We are also presenting a demo for this, so if you can join us in the demo session to have the overview of the different tools and experiments. Thank you.
Thank you.
Perhaps not as much as a question as an invitation to cooperate. We have a more commercial product. In a sense, it's open source. However, we solve similar problems as as you're solving with LDP. We have an industry session on Thursday, I think it is. But we solve things which may be reusable on the access control list and maybe also on push updates. And although our solution is vaguely different, I think a lot of the code could be reused, and maybe we can cooperate.
Yeah, yeah, okay. Because, like, for now, as you see, the language is very, very basic, because we have only included some like RDF source basic containers. So yeah, it would be interesting to see the different approaches to tackle access rights and so on. Thank you.
Hi. Have you estimated how hard it is to do the design? Because you said that part you still need, the human needs to design still based on the input TCAT, the LD document. For in your case that you were testing in, for example, how hard was it?
Well, it would depend on the source that you are considering. But because for now, the source that you have considered are only like TCAT data sets, and like quite, not simple, but we are aware of what's in the RDF graph. So if you are aware what you want from the structure of the LDP that you want from an RDF graph, it might be relatively easy. That's what we think. But before doing so, probably you would have to get an overview, what does the semantics of the language really, and then I think it would be not simple, I don't know, but maybe possible.
And another question would be, is it possible to get it wrong? Or I mean, what happens if I design wrongly and I run your thing? I mean, what the output breaks? You have some sort of detection that say, hey, this is not okay, or what happens in that case?
For now, we don't have any validation, but validation would be possible, for example, using shackle, describing forms of those. For now, we have not yet done this, so this might be included in the future works also. Yeah, thank you.
I have one question.
Yeah.
Who is the target of your language?
So it would be mostly data publishers who want to, like, they are obtaining data from data producers, and if in the ideal case, the data producers might provide the design that they are just going to use the sources from the publishers and the design and expose the data, probably, yeah. Okay, thank you.